Good afternoon, everyone. Welcome to this problem solving session. We'll start the session in few minutes so that many more participants can join. Hi Renuka, happy Holi. Renuka, are you there? Okay,
Sir, good evening, sir.
yeah, happy Holi.
Yeah, thank you, same to you, sir.
Yeah. Okay, we'll start our session since there are no other people, so I was waiting so that students.
Okay, sir.
So okay, so let's start the session without any further ado. Okay, so uh, so this is the problem solving session for the thermal physics course, and the instructor of the course is Professor Debamalya Banerjee of IIT Kanpur, and this is the assignment sessions for week number 9, and I am Dibyendu, and let's start the this problem solving session. Okay, so the first question says, uh, yeah. The first question says, which of the following is absolutely true? Option A, the entropy of any system always increases. Option B, the entropy of any system decreases. Option C, the entropy of the universe increases. Option D, the entropy of the universe increases but might also remain unchanged. So, Renuka, what do you think? First of all, from which laws of thermodynamics will be useful or will be applicable to answer for this question? Do you know that?
Entropy of the system is decreases, sir.
No, not necessarily. Sometimes the entropy of the system increases also. Let's say you guys are in a room, and now when you are just starting the your party, you guys are calm, so the entropy of the system is less. Now when now when uh, you are doing some stuff, you are enjoying, you are playing the music, the entropy is increasing. So that is one sort of systems entropy can increase also. So let me first tell me which laws of thermodynamics will be useful here. Tell me that. Do you know, or should I?
Sir, last option, I think.
Yeah, last option is correct, but my question is which laws of thermodynamics will be applicable for this, for answering these questions. Okay, no problem. I can Okay, so first law of thermodynamics tells you about energy conservations, but second law of thermodynamics is talking about entropy. And there you can see there are different statements for different statements for different people, but overall they say that uh, the statement is like this: entropy of a closed system is can can increase or remain same. Okay, so this is the sort of abridged version of second law of thermodynamics. So from here we can say that universe which can be considered as a closed system, so the entropy of that universe, of that closed system, the entropy of that universe increases but might also remain unchanged. So option D is correct. But before going into the things, so there are different statements I want to write, because there are different people who will be useful for that. So there are different kind of statements. First is called a German scientist Clausius, who tried to talk about the second law of thermodynamics, and this demon entropy is very difficult for those. It's difficult now also. So this Clausius statement, I will write about it. This Clausius statement says, so if you guys were careful or attentive in my last class, I also talked about few things when we are discussing the heat engine and these things. Heat can never pass from a colder to a warmer. Let me. So to a warmer body without some other change. Connected So main crux of this statement is that heat can never pass from a colder to a warmer body without any help or without any external work. So that's why you need electricity for the refrigerator. There are different statements also that for Kelvin, which is Kelvin statement, that was, let me write it here. It is impossible for self acting machine unaided by any external agency to convey it from any portion, convey it from one body to another at a higher temperature. Okay, so these are the kind of statements that people make to to first state different way to, sorry, okay. So these are the statement people use for people actually told about second law of thermodynamics, because it was sort of, it was difficult to quantify because people didn't know that much about entropy. That's why they tried to say which is fundamentally there or which was phenomenological, that heat can never pass from a colder to a warmer region without any help, and that can be also written from a machine perspective. There cannot be any instances where there will be perpetual motion, perpetual machine that can do the work on your own, on its own. So means you are providing Q1 from a heat engine perspective. You can say that Q1 heat as being absorbed from heat source, and then W amount of work has been done, and then again Q1 amount of work has been thrown to the sink. That cannot be possible. You cannot get any kind of work with, cannot get any kind of substantial work uh, with exactly throwing that amount of heat that you have been absorbed from the source. So that is one kind of thing. So this is the difference to test statements, Clausius and Kelvin. Okay. So next problem. So the next problem says the change in entropy of 1 mole of van der Waals gas is given by something like that. So to there are different TDS equations. So you have to know those TDS equations. I will write one first TDS equations. So the first TDS equation says TDS is equal to du plus d, let me write it pdv. Okay. Now here we have to do something because uh, there are certain difference compared to the compared to work done in ideal gas system, because here internal energy is not only a function of volume, a function of temperature, it's also function of volume or pressure. So the van der Waals gas equation, this van der Waals gas equation, it says P plus A by V square. I'm writing for 1 mole, V minus B is equal to RT. So you can write P is equal to RT by V minus B minus A by V square. Now we can write any differential ds. Since ds is a function of t and v, we can write ds as ds dt at constant v dt plus ds dv constant t dv. Okay. Now if you write TDS, then it will become T ds dt constant v dt plus T ds dv constant t dv. Now we have to use Maxwell relation. There are 4 Maxwell relations, but to remember it mnemonically. So in this way, if you differentiate, that will be positive, but in this way, this will be negative. Okay. So then del S del V, del S del V. So this is a Maxwell relation. So del S del V at constant t will be del P del T at constant V. Okay, so this thing will be changed. Now del S del T at constant V, we have to play around this a little. Okay, let me write it. Now for so you know this TdS is equal to du plus PdV. Now if that is the case, then what will be T ds dt dt at constant V? If V is constant, then dV is equal to 0. So this will be du, this will be delta U delta T at constant V. What is delta U delta T at constant V? This is heat capacity at constant V, specific heat at constant volume. This is CV. Now we can just change this thing and write it in terms of that. Okay, so T ds will be CV dt plus T dP dt at constant V and dt. Sorry, dV. Okay. Now you got this. Now P is RT by V minus B minus A by V square. Now if you get dP dt at constant dP dt at constant V, so this term is 0, only this term remains. This will be R by V minus B. Let me substitute this. This will be CV dt plus this will be T R by V minus B dV. Now we need to calculate a change in entropy. So that becomes ds will be CV dt by T plus R divided by V minus B dV. Okay. Now let me take the integration. So delta S interval change will be CV T1 T2 dt by T plus R V1 by V2 dV V minus B. This is log. So you can write in terms of this. Then you can write CV ln T2 by T1 plus R log V2 minus B divided by V1 minus B. Okay. So in that case, this is the correct option. So option B is the correct option. So let me go through these steps first. So we need to calculate the entropy change in the system for one mole. So for that process, what we have to know that to get the entropy change, we need to derive it from first TdS equation. What is first TdS equation? First TdS equation is TdS is equal to du plus PdV. That means the change in entropy times temperature is equal to the change in internal energy plus work done. Now for van der Waals gas, the gas equation is totally different. There, internal energy and entropy is not only function of temperature, it's also a function of pressure or volume. So, for van der Waals gas, for 1 mole, the equation of state is P plus A by V square times V minus B is equal to RT. From there, if you do the algebra, you will get the expression for P, which is P is equal to RT by V minus B minus A by V square. Now, since ds is a differential, to get a differential in terms of two other variable, which is a variable t and v, we can write ds in terms of ds dt. T, this is a multivariable function, right? S, which is entropy, is a function of temperature and volume both. We can write ds is equal to ds dt at constant v dt plus ds dv at constant t dv. Now we will use Maxwell relations. That for that I have written the mnemonic diagram at right, where SPTV written in this fashion. When you are going top to bottom, there will be no negative, but when you are going left to right, there will be positive, and vice versa, there will be negative. So if you go bottom to top, that will be different. Okay. Now you can write del S del V at constant t. Del S, let me show you. So okay, so del S del V at constant t is equal to del P del T at constant V. Okay, so if you write del S del V at constant t is equal to del P del T constant V, you can just transform here del S del V constant t in terms of del T del P del T at constant V dV. Now to get this del S del T at constant V, we have used a different okay, someone joined. So we have used different things. So when from first TDS equation, if we get del S del T at constant V, due to this constant V, this term P dV will be 0, because if V is constant, dV is equal to 0, so this term will be 0. So the only thing remains is dt ds del T del S del T at constant V is equal to del U del T at constant V. So what is del U del T and constant V? This is specific heat capacity at constant volume, because energy, how internal energy changes with respect to temperature at constant volume is specific heat at constant volume. Now we can write this thing is CVdT plus T dP dt V. Now we will get P in terms of this, and we will take the differentiation with respect to temperature since and keeping V constant. See, since V is constant, so this term will be 0. There will get RV by R divided by V minus B, and we have substituted that here. Now TDS, so we will divided the whole equation by T. So this del ds is equal to CV dt by T plus R by V minus V dV. Now if you take the integration, that will give me the change in entropy, that will be CV. So the limit will be T1 to T2, and that corresponds to V1 to V2. So dT, this is a logarithm of T, so this is ln T2 by T1, this is ln of V minus B, so this is ln, and we will put the limit, so this will be ln of V2 minus B divided by V1 minus B. So now is it clear? Is it clear, everyone?
Yes, sir.
Okay.
Yes, sir. Yes.
Okay, that's great. So this kind of for this kind of calculation, you need to play with different different equations altogether. So you need to know about van der Waals gas equations, you need to know about first TDS equation, you need to know about the Maxwell relations as well. So, so these kind of questions may come in your exam. So please be prepared with that, and please play around all those concepts. Okay, so that is important. So if that is clear, then let me proceed to the next problem. This problem says two globes contain 2 moles of oxygen and 3 moles of hydrogen gas at same temperature. So 2 moles of oxygen is there, 3 moles of hydrogen gas is there. A valve connecting two globes is opened So valve is opened, so the gas will be mixed. The gases are allowed to mix without any reaction. So there is no chemical reaction is going on, only normal mixing. Volume occupancy. Calculate the change in entropy given the universal gas constant is given there. So for that we'll use, so about the how entropy changes for mixing of gases, probably that has been discussed in the class. So uh, I will write the formula for I will write with the formula. So for any gas mixing, so remember, first thing, this is applicable. So mm, change in entropy for mixing is applicable for different gas. So if that was for same gas, this will not be applicable. There comes a different concept. I will talk about that in the next problem. So delta S mix is equal to N chi A ln chi A plus chi B ln chi B. There will be one minus here. So what is chi A and chi B? Chi A and chi B are the mole fraction. Okay. So mole fraction is the number of moles. Number of moles for certain gas divided by total mole total number of total mole of gas present in the system. So if that is the case, so for oxygen, for so N NO for oxygen, this is 2 mole, and in hydrogen this is 3 mole. So chi O2 will be 2 by 5 and chi H2 will be 3 by 5, right? If that is the case, then delta S mix will be minus N. Now N is total mole, that will be 2 plus 3 is equal to 5. So minus 5 divided by 2 by 5 ln 2 by 5 plus 3 by 5 ln 3 by 5. Now take just reverse of this, so this will be 2 ln 5 by 2 plus, okay, there will be one R universal gas constant R. So this will be R and R3 ln 5 by 3 joule per Kelvin. Now tell me the answer. So this will be, okay, so delta S will be 2R ln 5 by 2 plus 3r ln 5/3. So do the calculation and tell me the answer. What is the hello and R value is R equals to 8.31 joule per mole per Kelvin. Anyone? What is the answer coming? What is the answer coming? Anyone? Am I audible?
Yes, sir. Yes, sir.
So
Few
what is?
minutes. Wait.
Yeah. Please do.
Show me next page, sir.
Yeah, sure.
Sir, I think 26.74.
26 point. 2R there is 2R. But for my case, that is 3R is 5 by 3 is ln 5 by 3 is 0.5 and 3R is 24. This is coming out to be 12. 2R is 16. What is ln 5 by 2?
ln of 5 by 2 0.8047 or sorry sir.
0.91 times 16.62 14 14.95 14.95 and there is 10 12. It's coming out to be 27 7 is it's coming out to 27 is something like that. Okay, so
That's only tell you sir.
so you tell me
6 point something.
okay
20
27 point
26 point 26.6 sir.
yeah good. So this is the number. So and here none of the option is there, so you don't need, you need not to worry about this thing. So the correct option is this one. Correct answer is this one. Okay, so okay, uh, now for this thing I want answer. So I gave you one clue in the previous question. So two globes contain oxygen gas of 3 moles and 5 moles at same temperature. A valve connecting the two globes is opened and the gases are allowed to mix. Calculate the change in entropy given R is equal to 8.31 joule per mole Kelvin. So which option is correct? I'm just telling you there is no need to do any calculations. This should be done by just mere concept. Now I told you that for change in entropy for mixing is actually is applicable for only different gas mixing. For same gas mixing it is not applicable. That comes due to the Gibbs paradox. Due to the Gibbs paradox there will be no change in entropy when same gas mixes with with a certain amount mixes with a certain amount of same gas. Okay, so this is from concept perspective. So just know that. Okay, let me write it here. Change in entropy for mixing occurs only for different gas for same gas mixing. There is no change entropy so for this question delta A is be 0. So option C is correct option. So change in entropy for same gas mixing is 0. Okay, so let me read out the next question, which is an elaborative question. An isothermal curve and and an adiabatic curve in PV plane corresponds to dash dash in TS plane. So we need to find how isothermal curve and adiabatic curve looks in TS plane. Okay, so let me write it here. So first isothermal. Now this is P, this is P. Now for isothermal it is this, and T is fixed. Okay, this is PV diagram. TS diagram. So this is this. Now for isothermal process, temperature is fixed. Since temperature is fixed, so this will be a constant horizontal straight line parallel to the s axis. So first thing, this straight line parallel to s axis for isothermal, straight line parallel to s axis, this thing is. Now we have to talk about the adiabatic curve. Now for adiabatic curve, here for adiabatic this is more steeper. So if you write isothermal, this will be isothermal, this will be adiabatic. For adiabatic, dq is equal to 0, that means ds equal to 0, that means s is equal to constant. We will use this fact for our calculations. Okay, so for TS diagram, so s is constant, let me write 1s, take 1s. So this will be parallel to the t plane, t axis. So straight line parallel to the t axis will be correct. Okay, so in TS plane, isotherms will be parallel straight line to s axis, and in TS plane adiabats will be parallel to t axis. Okay, so this is easy. Now here there is another question which will be, no, two bodies of equal mass and thermal capacity of 0.8 joule per Kelvin, so Cb is given, are at temperature 100K and 200K. They attain the same temperature on being placed in direct thermal contact. Calculate the change in entropy. Now, if they are in direct thermal contact, what will be the final temperature for both of those objects? If they are in thermal contact, then what will be the final temperature for both of these objects? Yes, Renuka,
There are some little bit doubts, sir. Once again, you can tell me, sir.
please. What is the doubt?
Sir, I think 100 and 200 degree Kelvin. Sorry, 100 Kelvin and 200 Kelvin, sir.
Hmm. Now they are in
Normally, here,
now they are in direct touch. So what will be the
yeah, that
final?
means the change in entropy will be zero.
Why?
Anything same temperature?
No, change in entropy doesn't depend on, like, if there is always heat flow. So if there is some heat flow, so change in entropy will be there, right? Entropy change will be zero for adiabatic process when there is no heat exchange. So actually that is a good question, Renuka. That is a good observation. Why is the entropy change not being zero? That's a good observation. We'll see why it is not zero when we'll calculate the entropy. For now, please tell me, if there are two objects who are of different temperatures, they are in thermal contact, what will be the final temperature? This is easy, right?
Here, what formula are you using, sir? ds equal to dq by
No, no,
dt or
no, no, no,
the
no, 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 no. Not that much complicated. My question is pretty much simple. Two body of different temperatures, they are in thermal contact. What will be the final temperature?
the differences, sir?
Difference means their temperature will be similar, right? Since they are in thermal contact, after some point of time there will be in thermal equilibrium, their temperature will be same. Now if they are in thermal contact, their temperature will be 100 plus 200 divided by 2, right? Because they are of same mass, same heat capacity. The amount of heat, it the hotter object, the amount of heat it will release, the same amount of heat that that body which is cooler will take. So that temperature will be same. So that's a pretty simple statement to make. So let me write here. Since the objects are of same mass and thermal capacity, the final temperature will be TF will be 200 plus 100, 150 Kelvin. Okay. Now we have to calculate the change in entropy. Now what is the change in entropy? Delta S. Delta S will be of the same heat capacity. This is CV. This is T initial. Let's say this is hot. T hot to T final dt by T. This is for hot, and for cold del S del C. This will be CV, same CV, TH, T low, sorry, to TF dt by T. This becomes CV ln TF by TH. This becomes CV ln TF by TL. Okay, so please tell me. Uh, so CV is 0.8 joule per Kelvin. So after calculation, please tell me. So TF, T high is 200K, T low is 100K. So after up to the calculations and let me know the answer in comment box. I'm just I'll just take 1 or 2 minutes break. Okay. So please, I have given you the formula. So for one thing, for one body, it will be negative. Entropy will be negative. For one body, it will be positive. And if you add them, that will give you the final entropy. Okay. So please do the calculations. I have written the formula. I am coming. Okay.
Sir, option B.
Okay. Thank you, Renuka. So Renuka is getting the answer close to 0.09. Okay. So let me write it then. Okay. So here this will be CV is 0. This will be, for my calculation, it is coming out to be So this will be 0.8 ln 150 by 200, and this is CV ln 150 by 100. It is coming out to be minus 0.230, and this is 0.0324. 0.324. So total entropy delta S is equal to delta SH, delta S school will be 0.09, as this is 0.086 probably, 94. Oh, this is be 0.09494. Okay, so this is the correct option B. Okay, so next question says the internal energy of a system. So internal energy is given by U is equal to A P square V, where A is a positive constant. Find the equation of adiabats in PV plane. So for adiabat, okay, let me try by doing things. For adiabat means dq is equal to 0, means TDS is equal to 0. Okay, that is one information is given. And how internal energy is a function of pressure and volume, that is also given. So we will use the first TDS equation. So first TDS equation, so first TDS equation gives you TDS equal to du plus PdV. Now for adiabats, dq is equal to TDS equals to 0. That becomes du plus PdV equals to 0. So we are given this equation, du plus PdV is equal to 0. Now u is a function of A P square B. So that we can write u is equals to, u is a function of P and V, then du will be delta u delta P at constant V dV plus delta u delta V at constant P dV. So this will be dP probably. What is delta u delta P? A P square V. So delta u delta P is 2A P V dP plus del u del V. So this will be A P square dV. So this is equation number. So follow the process. First we have written the TDS equation. Then for adiabats we have put the change of heat or heat exchange is 0. From that we have got it u plus PdV is equal to 0, and then we have written the differential form of internal energy, and we got this. Then we substitute 2 in 1. If you substitute that, you will get 2A V PdP plus A P square dV plus P dV equals to 0. This is equation number 3. And if you can divide this equation number 3 by p. So if you divide it by p, then it becomes 2av dp plus ap plus 1 dv equals to 0. So you can write in terms of this. This is equation number 4. Now I will take v here and this here. So we'll get 2a by ap plus 1. So we'll get 2a by ap plus 1 dp plus dv by v is equal to 0. Now this is a differential equation. So by integrating we get, so this can be written in terms of, so differential of ap plus 1 is a dp. So we can write here in terms of 2d of ap plus 1 divided by ap plus 1 plus dv by v equals to 0. Now after integration we get 2 ln ap plus 1 plus ln v equals to 0. Okay. Now this is not 0, so this will be a ln of b, a constant, integration constant. Now we can write this one is ln of ap plus 1 whole square plus ln v, so 1 equals to ln b, and we can write in terms of ap plus 1 whole square v is equal to constant. So this is the equation of state. So ap plus 1 whole square times v is equal to constant. So ap plus 1 whole square times v equal to constant. So this is the right option. V times ap plus 1 whole square is equal to constant. So let me go through once more. So for this, since we have to find out the equation of adiabats in PV plane and the form of u is given, we have used first the first TDS equation which says TDS is equal to du plus PdV. For adiabats where the heat exchange is 0, dq that equals to TDS, that will be 0. That becomes du plus PdV, du plus PdV equals to 0. Now we know the form of u, we have to find the differential du. Now if u is equal to a p square v, we know then u is a function of p and v, then differential du can be written in terms of du del p at constant v dp plus del u del v at constant p dv. What is del u del p at constant v? If you differentiate with respect to p, this will be 2ap v, 2ap v and dp. And what is del u del v at constant p? If you differentiate u with respect to v, ap square will be there, so ap square and dv. Okay. Now I have put this du, the form of this du into this. So 2a vp dp plus ap square dv plus p dv. So there is, we can take one p out of this equation. That's why I have divided the equation number 3 by p, and we got 2av dp plus ap plus 1. So ap plus 1 dv. Okay. Now to solve this equation, we have just we have got differentiate with respect to divided with respect to 2av times ap plus 1. So for 2av there will be ap dp by ap plus 1. Sorry, excuse me. So there will be 2. So if you differentiate with respect to 2AV and AP plus 1, so there will be like this: 2A AP plus 1 dP plus dV by V, and after integration we got this 2 ln AP plus 1 plus 2 plus L ln V is equal to ln constant, and after the some algebra we'll get AP plus 1 whole square, V is equal to constant. Okay, so this is a quite simple problem. So I hope there is no other question. So let me proceed to the next problem. Next problem says, in a standard air auto engine, the air intake takes place at 1 atm pressure and at 30 degrees centigrade. Before the ignition, the pressure of the combustion chamber is 16 times the initial pressure. Find the compression ratio if gamma is equal to 1.5. Now, when this ignition process is happening, this is actually a adiabatic process. You know the adiabatic process follows P1 V1 to the power gamma equals to constant. Now using this, let me write it here. So for combustion, this is an adiabatic process. Okay. Now for adiabatic process, PV to the power gamma is constant. Now we need to find the compression ratio. So compression ratio is equals to initial volume divided by volume. Now final pressure is 16 times the initial pressure, 16 times of Pi. So from here please calculate. So for here, so from here you know that so let me write it here. Pi Vi gamma is Pf Vf gamma. Then from here Vi by Vf to the power gamma is equal to Pf by Pi, which is 16. So Vi by Vf, which is compression ratio, let me write it R, will be 16 by 1 by gamma. So 16 times 2 by 3. So what is the 16 times 2 by 3? Please tell me what is 16 times 2 by 3? 16 to the power 2 by 3. Renuka, what is 16 to the power 2 by 3?
Sir, 6.34.
6.34. Great.
I think option B, sir.
Option B, yes, you're absolutely correct. So this is 6.34 something. So I'll give it to 6.35. Okay, so that's that. Let me go to the next problem. So the next problem says, find the efficiency of a diesel engine for which the adiabatic compression ratio is 17 and the fuel cutoff ratio is 3.4, and take the compression the adiabatic coefficient is 1.4. So this is, you need to know the formula for this. This formula is for first is uh, let me define the different parameters here. So adiabatic compression ratio, which is Vi by Va. This is R, which is 17, which is 17 fuel cut off ratio, which is sigma rho. This is 3.4. This is R, and the formula of efficiency eta is equals to 1 minus rho times gamma minus r, and r to the power gamma minus 1 times gamma rho minus 1. So for my case, which is coming out to be 0.65. Okay, so this is just a formula putting problem, nothing to worry about. So you need to you need to know the formula for this thing. So uh, let me go to the next problem, which is the last, eventually the last problem of this system, of this session. The question says, calculate the efficiency of the cycle. Let me go to this. Question says, calculate the efficiency of the cycle ABCDA. So ABCDA, the total cycle, as depicted in the TS diagram given below, given AC is equal to BD. So this ABCDA is a circle. Okay. So please try to follow this concept, because this kind of problem will be there. Now, first question is, we need to calculate the efficiency. Now, how efficiency is calculated? Eta is equal to W by Q. That means work done divided by heat absorbed. Okay. Now heat absorbed means entropy increases, right? So entropy increases for this process. Heat absorbed means these two, sorry, this is the total heat absorbed. So we need to calculate this area, and work done is this area. Okay, this circle. Okay, sorry, it's too dry. So heat absorbed, which is Q, that will be first the area of this AC, this thing, so, and circular of this region, so semicircle area of ABCA plus area of rectangle, which is AC S1 S2A. So AC S1 S2A. Now for semicircle, this is pi by 2, and any BD or BD whole square, right? You can take it from here also, like T1 minus T2 is 50, S2 minus S1 is 50 also, BD square plus area of rectangle, and this one, this will be half of AS2 times AC. Now what will be the value of AS2? So it starts from 0, this is 300, this is 350, this is middle of that. So if this is middle of that, this is, so AS2, then it will be T2 plus T1 minus T2 plus 2. So T1 minus T2 by 2. If you write this, then this will be T1 plus T2 by 2. And what is AC? AC will be S1 minus S2 by 2. And what is BD? BD is this one, sorry, BD is this one, and BD is AC as similar. So BD equals to AC BD by 2. This will be BD by 2. So pi by 2 hours BD by 2. So this will be S1 minus S2 by 2, or T1 minus T2 by 2. Okay. Sorry, AC will be T1 minus T2. So AC will be S1 minus S2. This is wrong. So then Q will be pi by 8 T1 minus T2 whole square plus half T1 plus T2 by 2 by S1 minus S2. Okay. And if you write it here, then pi by 8, this will be 50 whole square plus half. T1 is 350, T2 is 300, so 650. So this will be 325 times 325 times 50. And W will be circular region. So this will be pi by T1 minus T2 by 2 whole square. So pi by 4 times 50 whole square. So for my calculation, it's coming out to be, for this process, 17,231.74, and for this process it is coming out to be 1963.49. So efficiency eta will be W by Q 963.49 divided by 17,231.74, which comes out to be 0.11. So this is the correct option. Okay, so that's the end. We'll recap some of the concept. If you have any question, you can ask, or I will recap.
The fifth question only you can once again show me, sir.
Which one?
Question number 5.
5.
Yeah, yes, sir.
I will show it one by one. Okay. Again.
Yeah, okay.
Okay. So then let's start. So first, the question talks about how the entropy of the universe will change. That's why we have used the second law of thermodynamics, and we have also discussed two different statements from two different scientists of different eras, Clausius and Kelvin statement, which are very much useful. And the main crux of second law of thermodynamics is entropy of a closed system either can increase or remain same. And for this is for universe, entropy of a, so this is entropy of the universe, you can say. So not closed system, I have just written it. This is entropy of the universe. Entropy of, so this is due to the Clausius and Kelvin statement. That means heat cannot flow spontaneously from colder to warmer body, and from Kelvin statement there cannot be any possibility to construct any self acting machine who can perpetually do some work. Okay. Now next we talked about the change in entropy for one van der Waals gas, and I have discussed it then and there elaborately. We have used first TDS equation, and again we have used the van der Waals gas equation. From there we got the we got the expression from pressure, and then we have written the entropy and its differential with respect to T and V, and we have substituted del S del V del at constant T using the Maxwell relation, which is del P del T at constant V. Let me write it Maxwell relation, otherwise you guys will forget. This is Maxwell relation. So I have substituted that for del S del T at constant V. We have used different method. We have used, since there is V is constant, so PdV will be PdV will be 0. So that's why T del S del T at constant V will be CV, and we have used that here, and after integration we have got this expression. For option for problem number 3, we have used the formula for change in entropy for mixing. That's why used, which is written by delta S mix is equal to minus N R. R is universal gas constant, and chi A ln chi A plus chi B ln chi B, where chi A and chi B are the mole fraction of two different gases. Here there are oxygen and hydrogen gas. For oxygen there is 2 moles, so their mole fraction will be 2 by 5. For hydrogen there is 3 mole, so the mole fraction will be 3 by 5, and total number of mole is 5. and after do the calculations, we'll get this value and this value. Now 4, for problem number 4, since this change in entropy for mixing is not applicable for same type of gas, means similar gas, means since here there are oxygen gas in two different container, so the formula for entropy for mixing will not be applicable here, because there will be Gibbs paradox. So for that, here delta S mixing entropy will be 0. So this is, Renuka, you are watching?
Yes, sir. Yes, sir.
Yeah, so this is the problem number 5 you have asked me. So for here the question says how an isothermal curve and adiabatic curve will be in TS plane. For isothermal curve in PV diagram, it will be like this. When T is fixed, isothermal means T's temperature is fixed. For TS diagram, since temperature is fixed, so the curve will correspond to a certain value of temperature. That's why it is at certain value and it is parallel to the S axis. That's why I have written that the isothermal will be parallel straight line to the S axis. So for different value of entropy, it will actually give you the same temperature. That's why it is isothermal. So for adiabatic curve, I have plotted it. It will be different from PV diagram. For isothermal, it will be more steeper, and its heat exchange is 0. ds is equal to 0. That means entropy is constant. And for that TS diagram, since entropy is constant, similar to from isotherm, it will be a parallel to T axis. Means different temperature corresponds to the same entropy. Is it clear now, Renuka? Hello. Is it clear?
Yes, sir.
Is it clear now?
Sir, now clear, sir. No
Okay.
problem, sir.
Yeah.
Thank you.
Okay. Now we have calculated for change in entropy for two equal mass and equal thermal capacity material, and we get first final temperature, and from that we have calculated their entropy change for hotter and cooler material, and we'll get two different entropy change, and we have added those things since entropy is additive, and we got this value. And here we got we have to find the equation of adiabates for in PV plane. For we have used first TDS equations, and for adiabates heat exchange is 0, dq is 0. We have used du plus pdv equals to 0, and we have used u is a function of p and v. That's why we have written du in terms of its differential, and we got a differential equation. We have solved it, and solving by we have got this. So this is an auto engine. This is we have to find the compression ratio vi vf. This is adiabatic process. After doing the calculation, we have got this. So here different parameters are given, and we have to find the efficiency of diesel engine, and this is the formula. We got this, and this is one thing where we have to find the efficiency. We know the efficiency is work done divided by heat absorbed from the source, and that's why we have first found the heat absorbed. Heat absorbed is this region, bigger region. So it is a region of area of this rectangle and this half circle. That's why we have written this. The half circle will be 5 by 2 of this half circle. So BD by 2. That's why BD by 2 square. And for this, it is half AS2. This is not half. This will be not be half. I have written nobody. So this will be not half. This will be AS2 plus AC. AS2 is written here. So let me. So after doing the calculation, I got this value, and for work done, this will be the area of this circle, and we got this value, and after that efficiency is 0.11. So that's that. So again, I will tell you, I would like to wish you a very happy Holi. Please,
Thank you, sir. Same
yeah,
to you.
and let me stop the recording, and we'll meet again in the next week on the same on Monday at same time.
Sir, I have